hear me? Okay. Yes, I wish I could find out the supersymmetry. So first of all, this is obviously not going to be a summary of the whole conference. This is I'm not competent to do that. I will just focus on the issue of supersymmetry and how we might find supersymmetry in the next few years. First, let's see. I would like to begin by thanking the organizers, Lars, Ulf, Ariel, Anupam, Jacob, Yashar, Linda, Anne, and sorry if I forgot other people who have made this a fantastic conference, and we enjoyed it a lot. I certainly enjoyed it a lot. It's just Okay. So the title of my talk is a question, and we are extremely fortunate that we may find the answer to this question in the next few years, thanks to this wonderful machine, the Large Hadron Collider, which will be beginning perhaps early next year. And it will probably mark the beginning of one of the most interesting periods in theoretical physics, perhaps rivaling the excitement of the 70s when the Standard Model was discovered. The LHC will push two frontiers, first the energy frontier and then the luminosity frontier. And relative to the tevatron, it will upgrade both of these frontiers by about an order of magnitude. It is expected that it will find the Higgs, the last particle of the Standard Model, and hopefully, we all hope, that it will also explore solutions to the hierarchy problem. Now, the hierarchy problem is, of course, very familiar to everyone here. It's the problem of explaining the 15 order of magnitude discrepancy between the Planck scale and the weak interaction scale. In addition, there is another equally big problem in theoretical physics, the so-called cosmological constant problem, which is the discrepancy between the weak interaction scale and the vacuum energy. Now, the challenge for theoretical physicists for the last 30 years or so has been to try to find natural theories, namely theories where both of these hierarchies can be explained naturally by dynamical mechanisms without any fine-tuning. This challenge has proven too big for dynamical mechanisms. In particular, there has been no dynamics that can account for the cosmological constant problem, whereas there has been a lot of theoretical ideas that have been proposed to address the gauge hierarchy problem. Many of them can be tested at the Large Hadron Collider. And here is a list of the various approaches to the gauge hierarchy problem. So first, the problem was first pointed out by Ken Wilson in 1974. It took about 4 years for some very smart people to understand what Wilson was talking about, and that led to the construction of the first solution to the hierarchy problem, which is the theory of technicolor proposed by Susskind and Weinberg. And this was a breakthrough moment for the community because that specific solution elucidated the nature of the problem and started the community thinking about other possible solutions. Indeed, problems with creating fermion masses and flavor change in neutral currents with technicolor led 3 years later to the construction of the supersymmetric Standard Model, and a few years after that to a set of other possibilities such as low-scale gravity, warped gravity, and most recently the little Higgs theories. What I'm going to be concentrating on in this talk is just the supersymmetric solutions to the hierarchy problem. So the first part of my talk will mostly focus on a brief overview of the supersymmetric standard model and its main experimental consequences. And the second half will deal with variations on the supersymmetric standard model that have been inspired by recent ideas on the landscape. So let me begin with a very brief historical summary of the 4 decades of supersymmetry and the types of developments that they have experienced. I have very little to say about the 70s, because the 70s were the very important era when the mathematical formulas for supersymmetry and supergravity was developed, but there was no physical theory that was consistent. In particular, attempts to build physical theories in the 70s led to charge and color breaking at the weak interaction scale. And in fact, it was thought that there was a no-go theorem that you couldn't break supersymmetry without at the same time breaking charge and color. This situation changed, of course, in the 80s with the invention of the supersymmetric standard model and its most important prediction, the unification of couplings. The 90s was perhaps the most interesting period in the history of supersymmetry so far. It started out with a big bang when around 91 Lepp discovered that the supersymmetric prediction of gauge coupling unification works far better than the non-supersymmetric one. And this was, of course, a high precision statement. So this created a lot of optimism in the early 90s that supersymmetry was just around the corner and it was going to be discovered perhaps by Lepp 2 or by the Tevatron. Unfortunately, as we know, these expectations did not materialize, and by the end of the 90s, neither Lepp 2 nor the Tevatron found either sparticles or any indirect evidence for supersymmetry. This led us in the new millennium, together with the cosmological constant problem, to challenge our concepts of naturalness. So in addition, these challenges received some support from the theoretical idea of the landscape and have recently led to a new version of supersymmetry that may have consequences for the Large Hadron Collider, which is called split supersymmetry, which will form the basis of the second part of my talk. So let me begin with the supersymmetric standard model. I don't need to review it for this advanced audience here. What it does, of course, it essentially doubles the number of particles by introducing a superpartner for every new particle. And of course, to solve the hierarchy problem and keep the Higgs mass at the weak interaction scale, supersymmetry has to be realized at the energy scale of about 0.1 keV. So particles must be at energies that are accessible at the Large Hadron Collider. The essential idea that allowed the construction of the theory in 1981 was the idea of softly broken supersymmetry, which says that you should parameterize supersymmetry breaking just as quark masses parameterize chiral symmetry breaking, and in so doing, you can do accessible physics at the TeV without knowing the inaccessible details of ultraviolet physics, perhaps near the Planck scale or the intermediate scale. So just as we can discuss quark masses without knowing what is the microscopic origin of the Yukawa couplings in any great detail, we can do supersymmetric phenomenology without knowing the origin of the soft supersymmetry. This is, of course, a very basic idea that underlies all of physics. It's based on the concept of decoupling that tells you that you don't need to know the microphysical details to do large wavelength physics. A good cook does not need to understand nuclear physics. All he needs or she needs to understand is chemistry. So one of the immediate consequences of the supersymmetric standard model comes from considering rare processes. Rare processes, most notably K-bar mixing, indicate that the soft supersymmetry breaking terms, in particular the squarks and the squark masses, must have a high degree of degeneracy in order to forbid flavor-changing neutral currents. So, in particular, squarks of the same charge and color must be almost degenerate to avoid disastrous problems with supersymmetric analogs of the GIM, Blaschko-Iliopoulos-Miami diagram, where you just take the internal lines and you replace quarks with squarks and gauge particles with BGs. And this is the interesting consequence that if we discover superparticles, they must be discovered in big groups. They will probably not be discovered in isolation, in big, roughly degenerate groups. So one should discover lots of particles at once, or nothing at all. The second implication of the symmetric standard model that was also immediately realized is that the stability of matter, the stability of proton, implies the stability of the lightest supersymmetric particle, which is an excellent dark matter candidate. And the way the argument goes is as follows. In the presence of new particles, new sparticles, such as squarks can mediate catastrophic transitions between a diquark state to a leptoquark state. Once you have diquarks turn into leptoquarks, you can cause proton decay by adding the spectator quark at a rate which is comparable to the weak interaction rate if the superparticles are at the weak interaction scale, as they must be in order to solve the hierarchy problem. So you need to forbid these dangerous couplings that couple single particles to pairs of ordinary particles. And the simplest way to do this is by introducing a symmetry. Today it's called R parity. Early on it was called family parity or family reflection symmetry. And the R parity effectively forbids the coupling of an odd number of particles into a vertex. And because of that, the lighter supersymmetric particle, a simple supersymmetric particle, cannot decay into pairs of ordinary particles. This is explicitly forbidden, and therefore is stable. Now, if the LSP, the lighter supersymmetric particle, is neutral and colorless, it is an excellent candidate for the dark matter of the universe. Furthermore, if it has a mass as expected around the weak interaction scale, as expected by the hierarchy problem, and it has electroweak interactions, then its thermal abundance, when calculated by standard freeze-out astrophysical methods, turns out to be in the right ballpark to be the dark matter of the universe. So this is a very nice aspect of supersymmetry that was not anticipated when it was first proposed to solve the hierarchy problem, but it came as a bonus, as a consequence of ordinary matter stability, the dark matter stability and existence of the candidate dark matter with the right abundance came as a nice bonus. So, of course, dark matter, as I emphasized, if the LSP is the dark matter, it has to be neutral and colorless, otherwise we would have seen it in a variety of experiments. It would manifest itself in heavy nuclei. During nucleosynthesis, there should be anomalous heavy nuclei that are formed by a charged or colored dark matter particle merging inside ordinary nuclei. So searches for things such as heavy hydrogen constrain the existence of anomalous heavy nuclei to about a part in 10 to the 30 and put severe limits on charged dark matter or colored dark matter. And of course many other more direct experiments. And it it also turns out that for theoretical reasons, the lightest supersymmetric particle is most naturally neutral and colorless, simply because if it had color or electric charge, the electric energy or the color energy, the energy stored in the fields, in the color or electromagnetic fields, would raise its mass and make it heavier than its neutral counterpart. Okay, so a very fundamental signature, a real smoking gun for supersymmetry is the following. When you collide two protons, say at the LHC, then because protons carry a lot of color, gluons in them, they typically give rise to colored particles such as quarks. Quarks decay into quarks and the LSP state. Quarks, of course, hadronize into jets, whereas the LSP, because it is neutral and colorless, is invisible. So it gives rise to famous missing energy or unbalanced momentum signatures, which, as we've noticed right now, come from proton stability. The proton stability, through the steps I outlined, lead to the missing energy signature that is the smoking gun, a smoking gun for low energy supersymmetry at the LHC. Perhaps now I come to the most important reason, at least pragmatic reason, for why today supersymmetry, low energy supersymmetry, is still the most popular candidate for a theory beyond the standard model, in spite of the fact that it has not yet been observed at like 2 or the teraton. So here is the famous gauge coupling constant unification plot. Let me start with the axis. The vertical axis is the inverse of the corresponding fine structure constant, and the horizontal axis is energy. So imagine that by doing precise experiments, say around 100 GeV, you measure the U1 and the SU2 coupling constants very precisely. Now, if you measure those two coupling constants very precisely, and you know the particle content of the theory between 100 GeV and high energies, then you can extrapolate from your measured value to see where these two lines of the coupling constant meet. And if you have unified supersymmetric theories, then the value where these two coupling constants meet tells you two things. It tells you where the theory unifies, the unification mass, and it tells you the value, the common value of the coupling constants where they unify. Now, if you have a fully unified theory, then the third coupling constant, G3, must also have the same value as the other two at the unification scale. Therefore, again, knowing the particle content, you can now extrapolate backwards. You can extrapolate backwards and find out what is the value of the strong coupling constant at 100 GeV and compare it against the experiment. This is the logic that tells you that you can predict one of the three gauge coupling constants in terms of the other two. This is simply a consequence of the fact that the low energy theory at 100 GeV has three parameters, the three coupling constants of U1, SU2, and SU3, whereas the high energy theory, because it is unified, it has one less parameter. It is characterized by the unification mass and the common value of the unified gauge coupling constant. Therefore, three numbers are expressed in terms of 2. This means there is a functional relation between the three low energy numbers. This functional relation is most conveniently expressed as a relation between what is called the sign of the weak mixing angle and the color coupling constant alpha 3. And the sign of the weak mixing angle is simply a measure of the ratio of the U1 divided by the SU2 gauge coupling. Okay? So the more, the better way to represent what the unification prediction for various theories are is in a plot that shows the weak mixing angle on one axis and the alpha 3, the strong gauge coupling on the horizontal axis, all measured at low energy. Okay. So here are the predictions, here are the bands of predictions for an ordinary non-supersymmetric grand unified theory, a la Georgia Glasser, for example, dating back to 74. And here is the corresponding prediction for the MSSM that was made in 1981. So this was now the state of affairs in 81. The state of affairs as far as experiments go in 81 was that very little was known, that both sine squared theta and alpha 3 were not measured very precisely. So there was really no strong preference between the non-supersymmetric and the supersymmetric grand unified theories. Nevertheless, there was some favoring of the non-supersymmetric possibility, but it was not statistically very significant. It was definitely not significant enough to discourage us from contemplating the possibility of supersymmetric unification. Now, when LEP turned on, of course, then we had a huge amount of data, and the situation changed dramatically. By the early 90s, the supersymmetric version was heavily favored to many standard deviations away from the non-supersymmetric prediction. And as time went on in 96, by 2006, the data essentially again favored heavily the supersymmetric version. And that is the state of affairs today. The widths of these bands, by the way, have to do with a combination of expected theoretical uncertainties due to unknown physics. For example, this particle spectrum is unknown at low energies, and also gut threshold corrections are unknown. So this blue band incorporates those theoretical uncertainties. The experimental uncertainties are significantly smaller than the theoretical uncertainties due to the unknown low energy particle spectrum and the gut particle spectrum. Okay, so this is the state of affairs. So here is a summary of the predictions of the MSSM. Degenerate soft terms, at least particles of the same quantum numbers, same charge, have to be approximately degenerate to avoid problems with rare processes, either K long, K short, or electronic rare processes. So many particles should be discovered at once in groups. Stable, like a supersymmetric particle, which gives an excellent candidate for dark matter and missing energy colliders as a smoking gun signature. Unification that I just talked about gives rise to proton decay, possibility of proton decay by dimension 5 operators. This is a big topic, I'm skipping it because there is limited time, but dimension 5 operators give rise to proton decay modes that are predominantly into kaons instead of pions, so that's another possible signature. But the most important thing is what I've already spent time on, the correlation between the SU2, SU3, and U1 gauge couplings is strongly favored the supersymmetric spectrum, beginning at around 100 GeV or a TeV all the way to the grand unification scale. So because this is already has been confirmed at LEP, it gives evidence that there are virtual particles from somewhere between 1 TeV to the grand unification scale. So, as I was saying before, the unification of couplings gave a huge boost to the idea of low energy supersymmetry, to the idea of the MSSM. So everybody expected that by the late 90s we should see sparticles. Nothing was discovered. No sparticles were discovered. No light Higgs was discovered, which is another prediction of the supersymmetric standard model. No indirect processes, flavor violation, CP violation, proton decay. No indication, direct or indirect, for supersymmetry. So here's the grade report, and what I believe is a relative objective grade report of the supersymmetric standard model. which is still valid today. It has two enormous successes: the unification of couplings, which is really a few percent success, and the dark matter, the existence and roughly the right order of magnitude abundance of dark matter. And it has several shortcomings. Where is the Higgs? Where are the particles? Where are flavor and CP violations that you would expect associated with a plethora of a priori independent physical parameters that the supersymmetric standard model can accommodate? Proton decay, as well as it also has some cosmological problems that can be cured. I should point out that none of these problems is deadly. And in fact, much of the activity of the last decade and more has been in trying to find ways to account for the fact that we haven't seen any of these signatures. And any one of them can be solved if you play with 10% accidents. It is the totality of all these things, the fact that none of these things has happened, that makes one suspicious that perhaps we are missing some part of the puzzle. Maybe not. Maybe it's all 10% accidents that make account for the fact that we haven't seen any of this. Nevertheless, it's interesting to ask whether there is just one principle or one idea that can address all of these problems at once, all of the shortcomings at once, at the same time preserving these two successes of the supersymmetric standard model, which I should emphasize, these are the two main successes of any attempt beyond the standard model. So it would be nice to preserve it. Now, if you look at the successes and versus the shortcomings, you notice the following amusing thing: that the successes of the supersymmetric standard model can all be attributed to the fermions, the gauginos and the Higgsinos. Can account both for dark matter and especially, and that's a very important point, for unification of couplings. The difference in the evolution of the gauge couplings between the standard model and the supersymmetric standard model is mostly attributable to the extra fermions, the gauginos and the Higgsinos, that the supersymmetric standard model possesses. Whereas most of the shortcomings are attributed to the scalars, with the exception of this cosmological. All of these flavor violating processes, for example, or the proton decay processes, are mediated by diagrams that have intermediate lines that are scalar. So if you could somehow close your eyes to the basic principle of hierarchy that gave rise to low energy supersymmetry, and erase the scalars and keep only the fermions of the supersymmetric standard model, you would have a very successful pragmatic theory that explains the absence of strange physics, of new physics, and maintains the successes of the supersymmetric standard model. And as we will see in a few minutes, that is exactly the attitude that is suggested by the theory of split supersymmetry. The theory of split supersymmetry will turn out to be nothing less than taking the standard model and adding the fermions of the supersymmetric standard model, the gauginos and the Higgsinos, down to at low energy. Nevertheless, instead of just jumping to that, I want to give you some potential philosophical or justification for taking that step. Before I do that, I should complete the list. There are two huge items in the list that I left out. Namely, one of the in the list of successes, I should add the hierarchy problem, which was the original motivation for the supersymmetric standard model. And to the list of failures, I should add the cosmological constant problem. And it is a point that is consistently, was consistently ignored by particle theorists for over 20 years in building models, including the supersymmetric standard model. The philosophy somehow was strategy for the last 30 years for particle physics, focus on this hierarchy problem, which is really a 30 decimal place fine-tuning, and ignore the cosmological constant problem, the vacuum energy problem, which is 120 decimal fine-tuning. Now, this reasoning might obviously be flawed. How? It could be that whatever principle solves this enormous cosmological constant problem can also solve the hierarchy problem at the same time. This is not a necessary condition because the vacuum energy problem or the cosmological constant problem is connected with gravity, whereas the weak interaction sector, the hierarchy problem, may not be directly connected with gravity. Nevertheless, it is a bit disturbing that we've been living under a gigantic shadow of a problem and focusing on what is relatively small problem. So the new attitude that is motivated in part from the absence of any evidence for new physics so far, direct evidence for new physics at the PED, and in part from the cosmological constant problem, is to take now the cosmological constant problem seriously and see if it teaches us any lessons. In particular, if you think about the vacuum energy, in theories with few vacua, it looks like the smallness of the vacuum energy by 120 orders of magnitude in Planck units, or if you wish 60 orders of magnitude in weak interaction units, it looks like that the smallness of the vacuum energy is an absolute miracle, a divine intervention. Why? Because any bigger value to the vacuum energy would rip galaxies apart. So it looks like someone who really cared arranged the vacuum energy to be just small enough so that galaxies would not be ripped apart and we would have a natural home to live in, namely galaxies. However, motivated by some early arguments by Andre, Weinberg essentially proposed a possible solution to this paradoxical divine intervention situation by the following argument. It's well known by now. By pointing out that if you have theories with a tremendous number of vacua, so the vertical axis is now potential energy in some horizontal space or some multiple field space horizontally. So if you have a tremendous number of vacua, now most of these vacua will have minima around the gut scale or the Planck scale or weak scale energy. But if you have enough vacua, then there will be some that will have just low enough vacuum energy to allow for formation of galaxies. Low enough vacuum energy that galaxies would not be ripped apart. Therefore, the requirement that there are galaxies, the postulate that there must be galaxies in order to have an observer in the universe, allows you to explain why we live in a universe with a small but not zero cosmological constant whose value is not very different than what we observe today. So this is usually called anthropic principle or environmental principle. In this case, we just postulate the existence of galaxies. We call it the galactic principle. So this galactic principle can account for the smallness of the vacuum energy. Now, this line of reasoning predicted, of course, within the right ballpark, within factor of 10 or so, the right vacuum energy, and has recently gained theoretical momentum because in string theory, we may well have a vast landscape of metastable vacuum. And we've heard a lot of talks about this, and this is associated with the fact that string theory has a lot of scalar degrees of freedom associated with all the different modes of vibration of the extra dimensions. And so you can easily have 10 to the 100th vacua, as recently emphasized by these authors, many of which are in the audience. In the presence of such an enormous landscape of metastable vacua, the way we do physics I should say the following. This is not a completely new situation historically. The first time that I know of that an analogous situation occurred was in the 1500s when Giordano Bruno postulated that there exist not many universes, but there exist many solar systems. And he even went so far as to postulate that there are many planets that revolves around these other suns and that living beings can inhabit these worlds. As you can imagine, this point of view was slightly controversial and led to the demise of Giordano Bruno in 600 when he was burned at the stake. This is also a warning for young people. It is strongly recommended if you want to work on the landscape that you have tenure. Otherwise, you run the risk of getting fired. So, coming back, the presence of so many vacua can drastically affect what we consider natural or likely, because now we enlarge our toolbox and we can use either statistical or environmental reasoning in arguing what is likely or natural. And here is an example of a statistical reasoning. Consider the usual idea of fine-tuning. In the presence of very few vacua, which is the case for ordinary theories, our normal measure for fine-tuning of the Higgs mass is that the degree of fine-tuning is related to the ratio of the square of the Higgs mass divided by the SUSY breaking scale. So as you push up the SUSY breaking scale to higher and higher, say to quark mass, then you have a finely tuned theory, 30 decimals or so. However, if you have a universe with many vacua, then there could be additional measure factors. In particular, there could be many, many more universes, many, many more vacua, where supersymmetry is broken at a high scale. And in that case, that measure factor may in fact favor high-scale SUSY breaking over low-scale SUSY breaking. And that is an example of a statistical argument that shows that maybe low-energy supersymmetry is not favored. Here is an example of an environmental reasoning. Just as the galactic principle, the existence of galaxies, solved or addressed the cosmological constant problem in a way that I discussed before, you can incorporate something that I will call the atomic principle, which can account for the gauge hierarchy problem and fix the weak interaction scale to be where it is. And the argument is very simple to make. So the existence of atoms can be used to set the weak interaction scale. And the argument goes as follows. Here I have an inequality that should be very familiar to you. This inequality is crucial for the existence of atoms. It's crucial for our existence. Mn is the mass of the neutron, Mp the mass of the proton, Me the mass of the electron, and E nucleon is the binding energy per nucleon in a nucleus, which is roughly 8 MeV typically. Now the first inequality guarantees that the proton is the lightest particle, not the lightest barrier. So it guarantees the existence of hydrogen. So to the extent that you believe the existence of hydrogen is important, it's a very important inequality. The second inequality is also very important. It guarantees the existence of heavy nuclei above the hydrogen, nuclei that contain neutrons. What this inequality tells you is that the neutron is not so much heavier than the proton that it can decay inside the nucleus. As we all know, a free neutron is unstable, but bound neutrons are stable inside nuclei. This would be violated if the neutron was much, much heavier than the proton. And much heavier means much heavier than the binding energy, than the nuclear binding energy. Now, it's easy to see that if you start varying the weak interaction scale, the weak interaction vacuum expectation value, you can violate both of these bounds. If you increase the weak interaction scale, if you decrease, the weak interaction scale, then the neutron becomes lighter than the proton and there is no hydrogen. Conversely, if you increase the weak interaction scale, then the neutron becomes so much heavier than the proton because it contains two downforce that heavy nuclei become unstable. In fact, there is a third regime. If you keep increasing the weak interaction scale much more, then the only stable barrier becomes delta plus plus. So you only have helium-like universe with delta plus plus as a nucleus. So that's also a weird universe where there are no ordinary atoms. So the requirement for having atoms, both hydrogen and heavy atoms that contain neutrons, sets the weak interaction scale within an order of magnitude or so of its present value. So in the presence of the landscape, both the previous statistical argument can suggest that the scale of SUSY breaking can be high, and environmental argument can set the weak interaction scale without any need for a dynamical reason for the smallness of the weak interaction scale. So now, armed with these ideas, you might say, well, perhaps these ideas suggest that we should just take the standard model and there is nothing else. We can use supersymmetry is a very high scale, and the weak interaction scale is set by atomic principles. However, the challenge is to construct, we know more than that the standard model is correct. We know that there are some successes of theories beyond the standard model. So we would like to have an extension of the standard model that preserves the successes, namely unification and dark matter. And the simplest model that we can build with symmetries now that is to just keep the fermions of the supersymmetric standard model and make all the scalars heavy. And that is the idea of split supersymmetry. So here is now the second part of my talk, where I'm now talking about the recent developments of 2004, namely the theory of split supersymmetry. So I start with the supersymmetric standard model. The supersymmetric standard model has just two scales, the Planck mass, or the Gatt scale, and the SUSY breaking scale at the TeV, which coincides with the weak interaction scale. Split supersymmetry is essentially the same with one very important difference. The SUSY breaking scale is now lifted, and it can be anything from 10 TeV to 10 to the 15 TeV. This is a free parameter. However, so the mass of SUSY breaking is there. So all the scalars, and namely squarks and sleptons, get a mass at the SUSY breaking scale. However, and this is the most important point, the fermions of the supersymmetric standard model, because they are fermions, they can be protected by chiral symmetry to be light. And so the Higgs-Zinus and the Gauge-Zinus that are fermions are protected by chiral symmetry to be light and be around the weak scale, and provide a candidate for dark matter, and also to provide just the right particle content to maintain the successful unification of couplings. And of course, the standard model Higgs is light because of the atomic principle that I advocated before. So this is the essential dynamics, the essential particle content of split supersymmetry. You see immediately that the only new particles you have at low energies in addition to the standard model is, of course, the Higgs-Zinus and the Gauge-Zinus, and the single standard model of Higgs, and all the squarks and sleptons are heavy. Now, how can we test this model? What about unification? Unification remains, Gauge coupling unification remains the same as before, the same as in the supersymmetric standard model, for the following simple reason. The only difference between SUSY and low energy SUSY and split SUSY is that squarks and sleptons have been pushed up in mass. But squarks and sleptons are complete SU5 multiplets. So to one loop, they do not affect the relative running of the gauge coupling constant. So the gauge coupling constants still continue to meet around the same point that they met before. So the prediction, the successful prediction of search square theta versus alpha strong is preserved. The gauge coupling constant is still new. How about all the problems of supersymmetry? Why haven't we seen particles, proton decay, etc.? Rare processes. The reason is very simple. The problems with particles, quarks and leptons, which is the vast majority of particles, are simply too heavy to be produced directly. Rare processes involve intermediate states that contain quarks and leptons, so they are heavily suppressed. For example, this is an EDM diagram or a flavor violation diagram if you add subscripts here. And so flavor violation, CP violation, proton decay are no longer a problem. And the reason for this is the number of new low energy parameters is greatly reduced. Why? Because all the quarks and leptons are heavy, and the vast majorities of the 100 parameters that the supersymmetric standard model has come from the quark and lepton set. So the number of parameters is reduced from about 100 to about 10. The gravitina moduli, which are cosmological problems, are also solved for a simple reason. These particles now become heavier and they decay. In fact, they decay way before nucleosynthesis, so they don't pose any potentially observable problem. They don't disrupt anything that we know about the universe. What about the Higgs mass? Remember, one of the puzzles was why hasn't the Higgs been observed? Now, in normal low-energy supersymmetry, the Higgs mass was expected to be in this neighborhood, about 110, because it's supersymmetrically related to the W mass. However, the split supersymmetry is somewhere in between. It's between ordinary low-energy supersymmetry and the standard model. So the Higgs mass now is somewhat heavier, and you can compute its mass, in fact, because the theory, remember, the theory is still supersymmetric at some high energy. So dimensionless couplings at some high energy are still related by supersymmetric relations. So you can actually make a computation of the Higgs mass, and depending on value of tangent theta, you can get it up to 160 GeV, but it depends on the scale of SUSY breaking, as you can see here. So it can be anywhere from 115 to 160 or so, depending on the scale of SUSY breaking. The bigger the scale of SUSY breaking, the heavier it gets. The most important direct prediction of split supersymmetry for the LHC is the following: is long-lived gluinos. Gluinos they have a lot of colors, so they can be readily produced at the LHC proton collisions. So you produce gluinos, and the gluinos, the only way they can decay is through an intermediate quark. They go to quark plus quark, quark subsequently decays to quarks and the LHC and gives missing energy. That's the decay mode. Very important point, the quarks now are extremely heavy. They are no longer at 1 TeV, they can be much heavier. Therefore, the gluino lifetime is long. So you have a particle that, if it weighs 350 GeV, which is not a crazy mass for the gluino, the production rate at the full LHC luminosity is 1 gluino per second, very hard to miss. And it decays with a lifetime that can be, well, it has a huge range because it depends on big powers of its mass and the SUSY breaking scale, but it can easily be macroscopic. It can be 2 seconds, it can be weeks, it can be a small fraction of a second, but it's definitely much longer than if the SUSY breaking scale and the quark masses were at TeV. So what are the signatures of this? Well, the signatures of this depend on what the gluino does after it is produced. And I will not go into the details of the story. When gluinos are produced, the very first thing, I'll just give you a rapid movie. Gluinos have color. You produce them, the first thing they do is they dress up. They grab either 2 or 3, either a Q-bar pair or 3 quarks, and they form or another gluon, and they form a colored singlet state. Oops, I'm sorry, I forgot to tell you a very important point. If you measure the gluino mass and the gluino lifetime, that gives you a measure of the SUSY breaking scale. Okay, keep that thought in mind. Now we go to where I was going. To produce a gluino, the first thing that it does is it dresses up into what is called an R hadron. It's either a meson or a baryon by combining with quarks or gluons. And neutral R hadrons don't stop. Now these are particles that weigh several hundred GeV, so they're like big bullets. They're hard to stop. In particular, they are hard to stop by strong interaction because strong interactions have a small range. But they can stop if they are charged. And to make a long story short, they easily get charged. If they are charged, they stop very easily within about 10 meters or so, depending on their initial velocity of production, by the famous beta block process, electromagnetic energy loss. And even if they are produced neutral, gluons give rise to neutral R hadrons. R hadrons can easily undergo exothermic reactions that are charge exchange. Because the pion is light, it turns out there are exothermic reactions that can happen and convert them into charged particles. Therefore, many R hadrons, many gluinos stop. And here is the calculation of the fraction of the number of gluinos that stop. Let's say at the LHC, if the gluino is about 500 GeV, or a million or so stop. And similarly, if they are heavier at 1100 GeV, somewhere between 10 to the 4 and 10 to the 5 stop. So many of them stop. Where do they stop? Well, they stop inside the detector, within a few meters inside the detector, typically in the hadronic calorimeter. So here is what happens. You have a collision. A collision produces a gluon. In fact, usually a gluino. Usually you get pairs of gluinos, but here is one of them. It stops inside the hadronic calorimeter, and then it can have a lifetime that may be milliseconds or seconds or days or weeks, and eventually it decays, and it can decay even when there is no beam running. We know that happens to be captured in the hadronic calorimeter can decay in the middle of the night when there is no beam time. And that is a characteristic signature. As long as there is someone to look for weird decays that happen even when there are no beam collisions, that is one of the characteristic signatures. And of course, the decay products are characteristic signatures that you can study. Even if the beam is running, you can look for horizontal jets, etc. So this is the most important. Now, there are several other signatures. For example, split supersymmetry, as I told you, has much fewer parameters than low energy supersymmetry. So you can make predictions, in fact, sharper predictions for some things, such as how you find them in dark matter detectors. So this plot shows you that upgrades, future planned upgrades of that, projected upgrades of dark matter detectors can test a big region of the split parameter space. By no means all, but a big fraction of the region. You can also have indirect dark matter detection. This is detection, this comes typically from annihilations that can happen between two dark matter particles somewhere in the galaxy, say near the cusp that is at the center of the galaxy. Such annihilations can give rise to monochromatic signals, and future experiments at GLASS can potentially probe for such signatures. Electric dipole moments, very rapid work. Usually, electric dipole moments in the supersymmetric standard model arise to one loop by a single squat or a single slepton. And these one loop diagrams are typically large by factors of order of 100 or so. So the absence of any CP violation is a puzzle for low energy supersymmetry. It's not a puzzle for split supersymmetry because there are no light squarks or sleptons. So the first diagram that contributes to electric dipole moment is actually two loops. So it's naturally suppressed by its additional factor of 100 without the need for any small, very small phases. So upgrades that are proposed to look based on atomic physics experiments to look for electric dipole moments of electrons are going to be sensitive to corrections that are expected in split SUSY with phases, CP violating phases of ordered unity that are naturally unsuppressed. Other split predictions involve the following. Split supersymmetry has the following dimensionless couplings. There are Yukawa couplings that couple the Higgses to the Higginus and the Wemos. There are 4 such dimensionless couplings. And of course, another dimensionless coupling is the Higgs-Porty coupling. Now, at the SUSY scale, all of these couplings are related by supersymmetric relations. They are dimensionless couplings. They are hard couplings, so they are sensitive to high energy symmetry. Therefore, they are related to each other and they are given in terms of a single parameter. At the scale of SUSY breaking, they are all given by a single parameter sine beta. So 5 dimensionless coupling in terms of a single parameter sine theta means that there are 4 functional relations. As long as you know the scale of supersymmetry breaking, which you can deduce from the Guino lifetime. So here is a picture. Here is a picture of what I told you. So you measure at low energies these dimensionless couplings, 5 dimensionless couplings. You run them at high energy, and you find that they meet at the point that is the SUSY breaking scale that you can independently infer from measuring the Guino lifetime and mass. So such a test would be a dramatic test for split supersymmetry, and if you see such a coincidence, then it will be some indication that there may be high energy supersymmetry in the world that is not used for the hierarchy problem, just like it has not been used to solve the cosmological constant problem. So this is a brief summary of split SUSY signatures, the Higgs mass, Higginus and Higginus at low energies, but potentially accessible to the LHC. Natural dark matter candidate EDMs, Guino lifetime, that's a smoking gun, and non-trivial relation among all these couplings. So if we find all these correlations, it will be an indication for split SUSY or an indication for a fine-tuning mechanism in the electroweak sector that, in contrast to the cosmological constant problem, is not plagued with subtleties of gravity. So it will be a signature for a fine-tuning mechanism that does not involve gravity. So now let me summarize. We are entering an extremely exciting decade for high energy physics in the LHC. What may we see there? Well, of course, nobody knows. One possibility is that we will really discover low energy supersymmetry, perhaps the supersymmetric standard model or a small variant of it, or extra dimensions. And this would be amazing. This would be a triumph of the idea of naturalness. Of course, it will still leave the solution to the cosmological problem will still be puzzling, but as far as in the electroweak sector, it will be a triumph of naturalness. Another possibility is we'll discover split supersymmetry and verify perhaps in detail at the LHC and in the future at the ILC. And that would be an indication for the landscape, a picture of many different vacuums. Yet another possibility is that LHC will run and it will just discover the Higgs. And then we will really not know what to conclude. Have we been unlucky? Is the world low energy supersymmetric, but somehow there is a little bit of fine tuning and we just missed seeing the particles? After all, how else can you account for the unification of couplings and nice dark matter candidates? Or is it split SUSY and we just missed seeing? We won't know what to conclude. We will be very frustrated. The only thing that we will know for sure is that we need more money. And we will need more money to build the next machine. But it is doubtful whether we'll find willing donors at that point. Finally, best of all, we'll discover something that nobody has ever dreamed of. Thank you. Let's thank again the organizers. One applause for the organizers. Yes, please.
Going back to one on the very early parts, you showed the binary angle and the strong force offset. And then you also showed the geometric data, which is very far off from the standard model. Does that mean that the standard model particle physics is zoomed out for that concept?
No. Depends on what you mean by the standard model. For example, you can take the standard, it means that you need something beyond the standard model to account for the convergence of the couples. That something may be supersymmetry. In other words, something that happens at a TeV. Or it may be split supersymmetry. Again, something that happens implies new particles at a TeV. It could also be a completely random accident. It could be that there are some random particles somewhere at some intermediate scale, 10 to the 9, 10 to the 11 GeV, that accidentally happen to match the predictions that you would have had if you had this nice symmetric particle quantity. I cannot, of course, nobody can exclude the possibility. By throwing random particles in the desert, which is somewhere between 100 GeV and 10 to the 16 GeV, just sprinkle random particles with different color and SU2 and SU3 and U1 quantum numbers, you can imagine that occasionally the predictions of the very symmetric theory are accidentally realized. This sounds unlikely, but cannot be excluded. It definitely implies something new. It does not tell you that that something new is necessarily at low energies. And the reason for that, incidentally, is because the RG running is sensitive to the logarithm of energy ratios. And the logarithm of energy ratios is independent of the scale where the new particles that you put is. So the new physics could be at some inaccessible scale. Of course, it's very unappealing. It would be a very odd accident if some random particle content that you throw in reproduces the SU5 predictions miraculously.
Our hadrons are wrongly criminals, the neutral one.
I cannot hear you. The hadron?
The neutral are hadrons containing the wrongly criminals in stations.
Yes.
Can they be stopped in, say, a kilometer of ice?
You mean even the neutral ones?
Yes.
They will stop much faster, and I'll tell you why. Yeah, they stop much faster because they undergo this charge exchange interactions. You see, you already know from experience with your body and radioactivity that within 10 meters there will be some strong interaction. And there is this exothermic strong interaction, I'll tell you. So every 10 meters or so you will have some strong interaction. Now, a typical strong interaction that you will have will not give you enough momentum transfer to stop this particle. Why? Because this particle is like a bullet. It has a big mass, and even if it has a velocity of order of 10 to the minus 2 or something, it carries big momentum. So a typical strong interaction will be a very soft process. But half of the time, that soft process will involve charge exchange because of isospin symmetry. The moment you do charge exchange, your cross-section becomes electromagnetic. And then you will stop within the plot that I showed you, 1 to 10 meters.
The reason I ask is, of course, these are being made in the atmosphere all the time if they exist by cosmic radiation. You see the combination of flux from short-wave heavy flavors which are being made. They will be made by the same process, go on feeding. And so if they make it down into, say, the ice directly, you can see the band that you're producing in the decay.
That may be, you see, the problem with cosmic rays experiment is flux. In other words, the vast majority of all, the reason why we build the LHC is not just energy, it's luminosity.
I understand.
And the problem with the vast majority of QCD involving processes is that they are peripheral. So if you have a typical collision, let's say you have some particle, cosmic ray particle collides with a proton, the typical cross-section is 30 millibarns and it involves epsilon, very small momentum transfer, and the particle just roams forward. And the ratio for having a 30 millibar cross-section versus an inverse TeV squared cross-section is like 10 to the 7, it's the ratio of the energy squared. So only 1 in 10 to the 7 of these collisions has a chance of being hard enough to start probing TeV physics. So production of such TeV particles will be very rare. Right. Yes. White is not much smaller, you mean? No. Why the vacuum energy is not much smaller than what it is? Yes. It could be. It could be, but I'll give you a couple. Well, here is a very simple argument. It is so hard to design theories where the vacuum energy is not enormous that you expect that there is a much bigger measure, a much bigger number of theories that have large vacuum energy than small. Therefore, you expect that we are essentially at the limit. We have a vacuum energy as large as possible that will tolerate or that will let galaxies form and not be ripped apart. So that is a natural expectation. You see, if you have a theory of measure of distribution of vacuum energy, which is sharply picked near rho equals 0, but really at rho equals 0, not 10 to minus 3 e to the 4th, but rho equals 0, then it would be, that would be great. That would be essentially like it could be a statistical solution to the cosmological constant problem. Of course, it would contradict the fact that we've actually measured the vacuum energy to not be much smaller than close to the maximum of what it should be for us to exist. Yes.